Hello and welcome. Good morning, good afternoon, good evening, depending where you are in this big world. Thank you for joining today. We're going to talk about avoiding measurement error traps with Real3D measurement. And so before we do that, I just wanted to go over a couple of housekeeping items. You'll notice at the bottom of your screen you have a number of different engagement tools that you can use. You can resize those and move them where you want to. A newer tool is called a reaction tool. So you can even give us a thumbs up or a wow or a hand clap, just to kind of get your perspective out into the chat here. Please also just make sure that you are taking a look at the Q&A section. You have questions, please type those questions in there. We'll get to those at the end. We'll try to answer every question. We do record this and then send this back out. So any questions we can't get to, we'll work on getting those answers out, or you can reach out to us directly. And please take some time to do the survey. It helps us understand if the content we're delivering is the content that you would like to listen to and learn about. So please take some time to do that. With that, I'm going to go to the next slide here and introduce a couple of folks. Clark Bendel. Clark spent the last 25 years in this RVI business developing with a focus on image processing, and really has masterminded a lot of the 3D measurement that you're going to learn about today, as well as our image processing. We call that TrueSight imaging. And then also Tom Danvers. So Tom is a 20-year veteran borescope inspector in the aviation space, knows the insides and outs of engines as good as probably anybody in the world, and is now heading up our software team on the product management side. And so will be a big part of explaining some of the technology we have today. And so with that, I'm going to hand it over to Clark Bendel, who will take you through our agenda today and kick things off.
Thank you, Tom, and thank you all for joining us today. So just a quick check of the agenda. We're going to start with kind of a deep dive on our 3D phase optical tips and how they compare to each other. Then we'll talk about some probe holding aids and get into a couple of our more advanced measurement types, area depth profile and blade tip clearance. And then we'll introduce a new measurement tool called radius gauge. It can be used to help with blade blending. You'll notice that we're not going to be getting into the basics of Real3D technology today. So if you need a refresher or if you're new to that technology, you can take a look at prior webinars that are linked in the related content area of your console and get some of that background information. So before I dive into the tip discussion, I wanted to revisit a slide that we showed in the last measurement webinar, listing some common sources of measurement error. So capturing the image from too far away is a very common problem. These are triangulation-based systems, and with any such system, the accuracy is going to decrease significantly as the tip-to-target distance increases. So one of the most important things you can do to improve accuracy is to get closer. Next, having insufficient 3D data quality for the measurement you're performing. This is especially true with depth type, small depth type measurements. It can be caused by capturing the image from too far away, but other factors like surface finish, glare, reflections, etc., can also degrade the quality from any distance. Using the wrong measurement type can lead to mistakes like missing the highest or deepest point, or perhaps measuring on a diagonal. And incorrect cursor placement is a common problem. If you put the cursors in the wrong place on the 3D surface, you will get an answer, of course, but it may not be for the dimension you actually wanted to measure. And we see this quite a lot with area depth profiles, so we're going to be talking about that a bit. So as we get into the tip discussion, keep these first two bullets in mind. Those are the ones that can be primarily affected by tip selection. So 3D phase was introduced back in about 2009 on the XL G3 platform. And the original tips that we offered were a forward general purpose black tip and an accompanying side view blue tip. These both have a 105-degree field of view and a depth of field of 7 to 8 to about 250 millimeters. So these tips work great for general purpose inspection. They give a nice full screen, high quality image, and then provide measurement on demand capability with the structured light projections. And so a lot of our customers will do an entire inspection using these tips rather than non-measuring tips. However, we do have a lot of customers who have to measure some really small features, and to improve that capability a bit, we created an orange version of the forward tip. Looks very similar to the black tip, but would have an orange color dot, and its optical depth of field is 3 to 120 millimeters. Next, we wanted to extend the measuring capability on the far end, so we created a side view green tip. This one has a near depth of field of about 15 millimeters. And just recently, we had a customer who was using a black tip, and they were really pushing the capabilities of that tip on the far end. And so we created a yellow version of the forward tip, again, very similar to the black, but here the optical depth of field is pushed out to 15 millimeters on the near side. So one of the biggest factors that limits the range capability of these tips is the spacing between the two groups of LEDs in the tip. So if we take a look at the relative spacing between these different tips, the forward view tips are all the same, so same mechanical configuration. The side is slightly less because of the different LED orientation. And then the green tip has 2.3 times the spacing between those LEDs. And that gives it a lot longer range capability. Another factor that has a big impact on the measurement range is the optical brightness. So if we look at this, the black and the blue as our standard, the orange tip is only about half as bright optically. That's because we had to use a smaller aperture to achieve that 3 millimeter near depth of field. And so that lets in less light to the sensor. The yellow and the green tips both have larger apertures. So these are both 60% brighter than the black and the blue tips. And so that is what gives the yellow tip a bit more capability compared to the black. And with the green tip, we're combining that larger LED spacing with the larger aperture, higher brightness level. And additionally, the LEDs in that green tip are larger and give us a little more output capability. So you put all those factors together, and it really makes that green tip a lot more capable, especially when trying to measure far away. There is, of course, a bit of a trade-off for that extended range, and that is that the tip had to be made longer to get that LED spacing. So it's about 14 millimeters longer than the forward view tips, about 8.5 millimeters longer than the side blue tip. So that extra length will limit its usability in some applications. So another sort of interesting way to look at the capabilities of these tips is through what we might call a measurement envelope. So here we're sort of showing the capability of the tip in terms of standoff distance along the horizontal axis and feature size along the vertical axis. So if we come in here toward the left lower region, where the feature size is very small and the standoff distance is also very small, you see that the orange forward view tip is coming in and is going to do the best job of measuring those small features when you can get close. However, it's going to be the most limited on the far side in terms of its range capability. The blue and the black tips start out a little bit further away than the orange tip, but they can measure quite a bit further away than it can on the far end. And then the yellow tip starts further out, but has more capability again on the far end than even the blue and the black. And then the green tip just has a much larger range capability than any of these other tips. So, you can get out 2 to 3 times as far with similar data quality with that green tip. Also notice that even within the working range of the other tips, the green tip is going to be able to measure smaller features at a similar accuracy. And that's because of that wider LED spacing and high brightness optics. It's just going to have less noise in the 3D data. So that's going to enable better measurement of smaller features from those distances. So, pretty much any time you can use the green tip, that's going to likely give you the best measurement accuracy. If you need to use a forward tip and you're measuring at a distance that's pushing the limits of the black tip, this new yellow tip might be a great option for you. And if you have to measure a lot of small features and you're able to physically get that tip in close to those features, then the orange tip is going to be a really good choice. All right, so next we're going to take a look at some comparison images. And for that, I'm going to go ahead and share my desktop. So we'll start out looking at just some 2D images. So here we have a dent or nick in the leading edge of a turbine blade. And this is looking from a distance of about 4 millimeters or so. This is the orange forward view tip with that close depth of field. So you can see we get a nice sharp image, clearly delineated features. And so this would be a nice tip for working at this range. If we switch to the black tip, you see it's quite a bit more blurry because the black tip's near depth of field is further out. You could still probably measure the depth of this feature using the black tip, but if you wanted to measure the width or the length, it would be pretty hard to determine where to place those cursors. So not as good an option as the orange tip there. And then if we switch to the yellow tip, which has that 15 millimeter near depth of field, you see we're getting quite blurry. So you probably wouldn't want to try to measure this feature from this distance with the yellow tip. Moving to a far viewing scenario, here we're in the combustion chamber of our CFM56-3 engine. And with the orange tip, we get a pretty decent view of the chamber, but the colors are a bit muted and the detail level is pretty soft. And that's because of that small aperture in the orange tip, which is going to reduce the optical resolution and cause the camera to operate with a higher gain level. And at those higher gains, we reduce the color a bit and reduce the edge enhancement to keep the noise in check. So a little bit on the soft and muted side. Moving to the black tip image, you can see we get quite a bit more color and we also see a lot more detail. It's just a much sharper image than we get with the orange. So much better for, inspecting these larger areas. And switching to the yellow tip, which has the even larger aperture, it has even higher optical resolution and more brightness. So we get a small increase again in the colors and the detail level that we see with that orange or with that yellow tip. So switching now to some 3D comparisons, I've got the handset application running on the left side of my screen, and this is our Inspection Manager app on the right side. So this is looking at the nozzle guide vanes in the same engine from the combustion chamber side. The MTD at this measurement point is about 60 millimeters, so we've got a range of maybe 40 to 80 in this scene, which is pretty far out for these tips, just to show the differences. And if you look at the point cloud view with the orange tip, you see that there's not a lot of data coverage. We're getting a little bit on the front of each nozzle guide vane, but very little else. And the data we're getting, especially on the farther one, is quite noisy. If we look at the black tip in pretty much the same scene, you see that we get significantly more data going back to a farther distance. And the data that we have is quite a bit less noisy than we have with the orange tip. And that's due to the, twice the optical brightness of the black tip versus orange. So if we switch now over to the yellow tip on the left side here, you can see that we get even more data than we have with the black tip. So going back quite a bit further on this vane and in the top area. And the noise levels are significantly lower as well with that yellow tip. So that optical brightness difference, that 60% increase, does give this yellow tip some enhanced capabilities, even though it's the same, mechanically, same projection geometry. So those are the forward view tips. Now let's take a quick look at a 3D comparison between those two side view tips. So we have the blue tip on the left, and then we'll take a look at the green tip on the right. So starting with the blue tip, and this is toward the front end of the compressor, pretty large blades in this section, and they're quite shiny. This engine hasn't had a lot of runtime. So this is a challenging situation for 3D phase with that shiny blade. And you can see in the point cloud view that we have pretty limited data with the blue tip, and the data, especially if we look back at this far blade, it's very noisy. And so this is really beyond the range where you typically want to use the blue tip in this kind of scene. If we switch over to the green tip, you can see that the data quality is much better, and we have a lot more information, a lot more data on the two blades here. And so this is kind of what you're going to see comparing these two tips at different distances. It might not be quite as dramatic at closer distances where the blue tip's going to do better, but you're always going to have a bit of a difference between the data quality with the blue tip versus the green, with the green giving lower noise levels than the other tips at a given distance within its capability range. So really good option where you're able to use it. Okay, so with that, we'll switch back to the slides. And here we have a poll question we're hoping you can answer. So based on this overview, do you think you or your business would require additional variants to fulfill your needs? So please check any and all of these that might apply. I'll give you a few seconds to make your selections. As we're thinking about what we might do in the future, we like to obviously get input from potential users to make sure the things we're working on are going to be useful. Okay, let's go ahead and take a look at the results. So it looks like we have a good number of customers who would like to see tips that can work at more extended ranges, both near and far, and perhaps some additional options for 4mm probes. All right, very good. Appreciate that feedback. All right, so next I will turn it over to Mr. Danvers, who will take you through some probe holding aids.
Thank you, Clark. I wanted to start talking to you really about this image here. I'm going to just play a short video. It won't come across as a smooth video rolling frame by frame on your, because I'm powering or transmitting over the net. But what you see here is, and I'll stop it at certain points, are points upon which the LED array firing off the fringe pattern from the LEDs from, in this case, the 3D phase measurement side-facing tip, the green tip, is projecting onto the surface, and as I pause it again through the clip, it's acquiring the signal back onto the detector in a matter of milliseconds. Over the course of essentially 2 seconds, the LEDs have fired, the white light has extinguished, and the sensor has received the appropriate information back onto the detector. It's a very quick process, and one that really doesn't cease to amaze me, really. Wanted to kind of draw your attention to the fact that there is a period of time required in order to collect the data. And we're talking to you about this because regardless of which sensor or which tip you have fitted to your video scope, a period of time is required for you to have the probe stationary such that the signal that you're getting back onto the detector is of good quality. So fixing and gripping and keeping your probe stationary during this essentially short period of time is very much needed in order to reduce the noise in the signal that you get back onto the detector. Pretty much holding the probe by hand, provided the probe isn't up against a surface, perhaps within the engine or the asset that you're inspecting. If it's held in free space, the probe is typically still going to be shaking because our hands aren't as still as perhaps they should be. So holding and being hands-free, or perhaps having the probe up against a surface such that it's not vibrating and shaking in air, is what's required. So what I'm showing you here is some information associated with some probe grippers. We recently made some adjustments to our probe gripper, the orange device that you see on the screen. It includes this 1/4 inch, 20 mil long insert that enables it to be attached, in this case, to the adapter, which is fitted to the Manfrotto Magic Arm. So by holding the probe and grasping it within the gripper and holding it in place with the Magic Arm is a very good way upon which you can keep that probe still. And so we have grippers for the 3 variants of insertion tube diameters that are typically used, 4, 6, and 8 mil. The alternative way to holding that gripper is on the lower right-hand side of this slide, where you have the clamp clamped up against the gripper, rather than using the insert to attach it to the Magic Arm. Either way, it's a good user-friendly way of flexibly orienting your probe to align with your access port and have that in place. The disadvantage, I suppose, of doing it this way, using the Manfrotto Magic Arm, is it's another piece of equipment that you have to take to the engine, assuming this is a gas turbine engine inspection that you're most doing. You're doing it out there in the field. Another piece of equipment can be considered quite bulky. The alternative is what we're showing here on this slide, is the probe holder, a very simple rubber part called the probe holder, designed such that you can pull it out of your pocket, in your overalls while you're on the engine, and press it into any given access port, essentially an access port that's less than sort of 10 millimeters or so. And as you push it into the access port, you'll see that it is designed to sort of compress and grip hold of the insertion tube passing through. So works really well with the 6 millimeter diameter variants, the 6.1 or the 6.2 variant of the insertion tube. Very good way that's compatible and mobile and portable and small, that'll work on pretty much most, if not all, of the access ports within a typical gas turbine application. Just drawing your attention to some of the details that you might find in the accessories catalog. So there's a series of documents that you'll see on your dashboard, one of which is this document associated with the accessories catalog. As you move through all of those accessories, lots of information in there. So please do have a look through that document. You'll see deep within that document is the adapter kit. So we have a series of threaded inserts that have common threads and pitches that are designed to work on numerous access ports across a large array of engine types. So these access ports are similar to the gripper and the magic arm arrangement that you saw me take you through earlier. The difference being no magic arm would be required. They're threaded into the access port. The gripper that you'll see holds on and tightens and holds on to the insertion tube, enabling you to essentially perform your inspection. And then when you want it to be held stationary in place, just twist the gripper and you can become hands-free, and both of your hands can operate and interact with the handset, or perhaps with the turning tool, for instance, and allow that footage and that inspection to take place with knowing that your probe is held fixed in place. All, again, just to draw your attention, all about acquiring the best quality signal-to-noise ratio from your measurement acquisition. Regardless of which tip you fitted, keep that probe stationary, albeit just for a number of seconds, a small number of seconds. In this case, really for the MVIQ, it's about 2 seconds. Keeping it still during that time will really maximize the quality of the signal that you return back on screen. Yeah, sure. I'll be taking you through some more measurement types shortly, but first of all, I'll hand you over back to Clark.
Thank you, Tom. Yeah, so before we get into area depth profile, we just wanted to show the complete suite of measurement types that we offer with Real3D. So the first 5 of these, length through multi-segment, you may have seen on older systems or with our traditional stereo measurement. So those have been around for a while. The last 5 of these are more advanced types that are specific to the Waygate Real3D suite. And the area depth profile and blade tip clearance and radius gauge are the ones we're going to talk about today. So now we're going to discuss area depth profile. So I'm going to share my inspection manager window here. So one application where area depth profile can be really useful is when inspecting or measuring orbital welds in pipes. So a common desire here might be to determine the maximum height of this weld. And in the past, one might have used a depth measurement to try to interrogate the weld. So one of the issues with using depth in this application is that it only gives you the height at one particular location. You also have to be pretty careful about how you set up the reference plane because of the pipe curvature. So, you know, it's pretty tedious to do a complete assessment of a weld using depth. Another option that one might use would be depth profile. So this is a little bit better than depth in that it will evaluate a complete slice across the weld at one location and automatically identify the highest or lowest point in that single slice. But again, when you have a long weld bead that you're trying to assess, it can be really tedious to try to do a complete assessment with the depth profile. So that's where area depth profile comes in and can be really useful. So with area depth profile, we're going to place 2 cursors on the parent surface above the weld, and the third cursor goes on the opposite side on the parent surface there. And the software here has mapped a reference profile line, which you can see is along the curvature of that pipe between those first 2 cursors, and then a parallel reference profile line passing through the third cursor on the opposite side. And this measurement is automatically looking at hundreds of essentially depth profile slices across this weld and looking for the slice that includes the highest or lowest value. And so it's identified this particular slice that's shown now as the one that includes the highest point, which is about 1 millimeter above the plane of the parent material at these locations. So to help visualize how area depth profile works, we have an option that you can choose called Run Demo. So when I click that, hopefully this comes through the webinar okay, but it's showing you a bunch of these profiles that have been checked to find that highest point along with their highest values. And you can see on the right that the reference plane indicated by the blue line or rectangle at the bottom is following along with the profile slice. So it's always tangent to the surface of the pipe at each slice location so that you're getting a perpendicular height from the pipe surface to the top of the weld. We can also show a cross-sectional view of the weld, and I'm just going to run that demo again with this perspective. So you get a sense for the shape of that weld. You can see there's maybe a little bit of a recessed region along the upper side of the weld as we go through this. So a couple different viewing options with the area depth profile. Another thing to point out, the green masking here, we call this the 3D surface mask. So as it's going through these individual slices, it's identifying points on the surface that are close to the reference plane for that slice, and it's masking those points in green for each slice. So basically, if a point is shown in green, that point is very close to the reference plane of one of these slices. And so as you see here, what you want to have is pretty good green coverage on the parent surface, and then really no green within the area that you're trying to assess. So that's an example of area depth profile on an orbital weld. So now I'm going to switch back to the slide deck for a moment. And let's take a look at some tips to help you achieve accurate area depth profile results. So first, and this goes back to the common sources of error slide, tip to target distance is very important, especially if you're looking at very small features. You want to get as close as possible, even a bit out of focus. Another indicator is that if the green mask is filling the region that includes the measurement point, which you can see is this green dot in this point cloud view. So if this green mask were filling that whole center area, that would be a sign that you're probably too far away and you should get closer and try to do another capture to better resolve that feature. Next, viewing angle can be quite important, especially again with very small features. So you're going to get the highest quality, lowest noise 3D data from a very non-perpendicular perspective. So you want to be at an angle to the surface rather than looking straight on. And that's especially true if it's a shiny surface. Next, if it is a very shiny surface and you're having trouble with 3D phase, you might consider using 3D stereo, which can be a little bit more tolerant of those shiny surfaces if there's enough texture there, and if you use that viewing angle to manage the glare, because you really don't want glare in the measurement zone with 3D stereo. Next, as always, when you're making measurements, you want to check the point cloud for noise that might be affecting your results. This is especially true with area depth profile because it's very good at choosing the tops or bottoms of noise bumps. So you want to make sure you're checking for that in the point cloud view. And especially for these smaller features, you want to make sure that the shape of that feature has been resolved and it's not just buried in a sea of noisy bumps. And finally, you need to make sure that you're placing your cursors properly when it's a curved parent surface. So as we showed in the weld example, and as we're showing here on the point cloud side, these are the first two cursors, and we have the curvature of the surface running between those cursors and in the line that's passing through the third cursor. We don't want the curvature to be in the direction of the slices that are going between those reference profile lines. We want that to be, you know, straight across the parent surface in that case. So with those tips in mind, I'm going to switch back here to my desktop. One second. And let's take a look at a couple more examples. Get this out of the way. All right, so I've kept the tips up on the left so that we can check these images against those suggestions. So here we're looking at, excuse me, the nick or dent in the leading edge of the turbine blade that we saw in the previous images. And let's sort of compare what we see versus the tips that we have on the left. So the first one is tip to target distance. Have we gotten as close as possible to make this measurement? So we see we're at about a 12 millimeter standoff distance. We know we're able to get closer even with the black tip and still have a sharp image, which we don't really need. We can be a bit out of focus. So I would say that we're further away than ideally we would want to be for this measurement. Next, how about the viewing angle? Are we very non-perpendicular, and is this a shiny area? So if we look at the glare, we can see that it does appear to be a shiny area, but our viewing perspective looks to be quite perpendicular. So we're not following that guidance in this case. So I'm going to skip the third bullet because this is 3D phase currently, and go to the fourth. Check the point cloud for noise and feature shapes. So let's go into measurement and switch over to the split view here and have a look at the point cloud. So we can see, do we see noise? Yes, we do. We see some bumpiness here that we would not expect to see based on the 2D image. We see some lumps in the parent surface. So we do have some noise, potential noise issues. And if we look at the shape of the surface, we're not really making out the pit or dent as we would expect based on the 2D image. So that's a sign that we're probably not getting a good result. Furthermore, you may notice that this is a positive result, and that's because we're picking up on this noise bump, which is above the parent material. And we've also, if we look at that green mask, we see we're not covering the parent material with that mask. And that is a suggestion that we may have incorrect cursor placement. And if we look at where the curvature is, it's in the lines running between the reference profiles and not in the reference profiles themselves. So just about everything that could be wrong with this measurement is wrong in this case. So an example of a lot of things you don't want to do. So let's take a look at a different image. Here we've switched over to the orange tip so that we can get nice and close. We're still in focus, even at a closer distance. It looks like we're non-perpendicular, so we have a better viewing perspective to reduce the noise level in our data. So let's go into measurement, and we're going to add the area depth profile. And let's make sure we place our two cursors going across the curvature. So now we see that curvature in our reference profile. And as we place the third cursor, we see it in that one as well. Now we have a negative result, which is a good sign, as we would expect for this type of feature. Looking at the 3D surface mask, we see we've got lots of coverage over pretty much the entire parent surface within the region between the reference profile lines. We also have an opening in the middle around the measurement point, so that's a good sign. And looking at the point cloud view, we don't see significant noise on the parent surface, looks nice and clean. We zoom that up a bit, we can see that the feature looks like it has the shape we would expect based on what we see in the 2D image. So by going through the checks listed in this tips list and making sure we're checking those items off, now we can have, excuse me, a much greater confidence in this negative 0.13 millimeter result, which is, I mean, honestly, this is getting to the smallest feature size that we would recommend measuring with our products. But here, because we've gone through all these checks and made sure we were positioned properly, we can have pretty good confidence in this answer. So that is our discussion on area depth profile. Now I'll switch it back over to the slides, and Tom Danvers will take us through blade tip clearance.
Thank you, Clark. Blade tip clearance is another measurement type available to you on the MVIQ. Developed a short number of years ago, I think it was 2 or 3 years ago now. It appeared on the borescope during one of the upgrades that we had. Blade tip clearance, as the name suggests, is a function specifically designed to measure and assess the overall clearance between the gap between the shroud liner or the abradable liner and the blade tip. And it's termed BTC, blade tip clearance, on your measurement tile screen. It's used for the 3D phase measurement tip, and it's really designed to be able to be optimized by using the long range 3D phase measurement tip, the green tip that we have in our portfolio. That enables you to gather both near and far field measurement information captured within the point cloud, so that the technology has the capability to also detect the edge of the blade and the perpendicular surface that is the abradable liner, and perform a series of many hundred images between those two surfaces and present the results in that simple text box that you see on your screen: minimum, maximum, and average. And yes, if you were to hold down on that text box for a number of seconds, it would switch from one unit to the other, in this case from imperial to metric, and vice versa if you held it down again. Just a quick way of transferring that unit to one to the other. As Clark was saying, really making sure that you've got the optics tuned, the optical field tuned to the scene that you're looking to detect. So practice, in this case, for blade number 1, in terms of getting your probe positioned so that you've maximized the scene that you want to measure before engaging the 3D phase measurement capture. I'll be running through a demo shortly on the borescope, but just going through some of those tips here before going through the demo. What we also have, if you were to press the image soft key on the borescope, you enter this page called the image transforms page. So you can adjust the brightness. You can also adjust the setting called dark boost that improves the clarity and the appearance of the overall scene, just in case perhaps the trailing edge or the far field surface of the aerofoil is dark, or too dark, for instance. So just to improve and optimize that scene. Again, from an angle perspective, what we want to achieve is not perpendicular to the blade edge and off perpendicular, just as Clark was talking about earlier with area depth profile. Works best in the compressor. Also, it does work in the turbine, but really it's suited for those abradable liners or seal segments that are not honeycomb seal segments. So, for instance, the CFM56HB turbine, I do know that doesn't have a honeycomb seal segment from the trailing edge, and you can so it does work in the turbine as well. But yes, really tuned for the compressor set of blades. Again, blade tip clearance is a measure of sort of compressor health. It's usually a step or an inspection that's taken place at various points through the life cycle of an engine. It's usually not instructed in the aircraft maintenance manual, but perhaps during pre and post lease of engine inspections, or post an arising in flight, for instance, heavy landing or engine surges, where there is a sudden shift in the axial displacement of shafts that can result in heavy wear and rub on the blades. So checking the condition of these clearances is something that can happen. So this is a measurement function that really does save a lot of time. Rather than doing individual depth measurements and then repeating those measurements on all of the blades, this is essentially a one-button process. So if I was just to now flick back to my borescope image, just one second. Just going to share with you my borescope screen and play a short video. So I've already captured blade number 1 and moved the rotor, in this case in the LP compressor or the booster of a CFM56 engine type, and pressed one button, which is the 3D PM capture. And you can see the scene. I've got both the near and far field in good view. And because I'm on auto repeat, it automatically selects blade tip clearance as the measurement type. So as you can see there, within a few seconds, it's analyzed the image. I've been able to press the save button and rotate and go to the next blade. What I have fitted on the probe here is the green long range tip. So you can see by the 3D surface mass that I've got a large amount of data present on the screen. So if I was to move to one of those saved images, in this case from blade 2, and then to the measurement state. Not that I was just really wanting to show you what is interactable. So all of those cursors are automatically applied by the device. And these two dotted lines represent the extremity upon which the tip of the blade tip data is taken from. The depth data are taken from that. So the fourth point from the depth aren't shown on all this slide. It's highlighting the front and the back of the blade that has been detected by the instrument. If I was to move the front and the back, the corresponding maximum and minimum value, it will adjust. So as I move, you can see the minimum value move, what you see, the blue line corresponds to the maximum value. In this case, is almost 3 millimeters, and that's projected along the length. And so you can kind of tell the difference between the maximum and the minimum of approximately 0.7 of a millimeter. So that distance diverging and separating as you move from the leading to the trailing edge of the blade. So blade tip clearance is a very, very useful, productive, very efficient tool upon which to carry out what would normally be a very time-consuming process. Again, using the green measurement tip really does enable this to take place in order to capture the full scene from leading to trailing edge and the full width of that abradable liner path that you see on the shot. So this is intentionally taken from the booster, where the blades are much more significantly larger than they are in the HV compressor. So it gives you a feel for in this case, the maximum target distance, well over 2 inches or 57 millimeters that you see here. another measurement type that we now have available on the borescope. This is something new. It came out just a number of weeks ago, so just wanted to make mention of it here on this webinar, is radius gauge. Radius gauge is a feature that enables the ability to place a circle of a known radius or diameter onto the 3D phase measurement or 3D stereo image that has been captured. The circle that you see, and once it's placed, there's a central cursor point, and that's the point upon which it can be moved around on the screen. I'll take you through a demo shortly. And so this is a feature. I'll tell you why this is why we've developed this. It's in as much that it enables you to assign confidence that the shape, in this case of a boroblend, the acceptance criteria for LEAP engine boroblends requires the shape to conform to an appropriate radius. That radius is a function of the depth of the blend. So I'll take you through a demo shortly. The assignment of these circles or radius gauges can be placed directly on the component or the point cloud of the blade in this case, or as per other measurements, you can make use of the measurement plane. So I'll just take you through that now. Press some buttons. So here again, I'm just showing my borescope screen and having loaded an image saved on my borescope. Recalled this image showing a scallop, a typical scallop blend in the center of what will be a compressor blade. You can see by the cursors already assigned a pointer line that measures the depth of this scallop blend as being just over 1.2 millimeters. And you can tell by the three other cursors, if I enter the measurement state, activate the image, so you can tell by the three other cursors that are on this image, showing you also the assignment of a measurement plane. So I've done that because I'm now going to add a measurement, select radius gauge, and you enter this keypad, or you're shown this keypad. And you'll see a series of the soft keys at the bottom of the screen have changed. One of them is reflecting the depth of the point-to-line measurement, 1.21 millimeters. So I'm going to apply a circle gauge into this image that is 5 times the depth of the blend shape. So the blend being 1.2 millimeters, multiply by 5. And as you can see on the keypad, there's a bit of a delay. It shows 6.05 millimeters, and press the Save Radius button. And you see the assignment of the circle presented to you on screen. The cursor is highlighted, so I can edit and move that circle. And because this is snapped to the measurement plane, you can tell with the point cloud on the right-hand side that it's snapping to the plane in accordance with that measurement plane. Just to demonstrate to you, this is, if I was to delete that measurement plane, that circle will now snap to the blade in the background. And so it's still of the same radius of a little over 6 millimeters, but it looks a lot smaller in size because it's presented itself on a surface that's much further away on the screen. So, the perspective is reduced so that you now can't, it's now no longer looks as large. So I'm going to go back and add measurement plane, bring it back into shot. Once I've got all those cursors activated, there we go. So it's brought the radius gauge back onto the plane of the blade. So just activate that. There we go. Now, also in accordance with the boroblend task for LEAP engines is making sure that the shape not only is equal to or greater than that radius for the depth of that blend, but also you can, it's a requirement to make sure that the lead out of the blend also conforms, in this case, to twice the depth of the blend. So 2 times, in this case, 1.2 millimeters. So again, like other measurements and other functions on the borescope, you can assign multiple measurements to the screen. So I'm going to just move it and make sure and place my radius of 2.4 millimeters against the lead out of this scallop blend, and just determine whether or not the shape of that lead out is tighter or shorter than the 2.4 millimeter radius. In this case, it hasn't. So kind of just showing you an example here of an acceptable scallop that exceeds the minimum radii of 5 times and 2 times, being the depth of the blend in the center of the blend and all the lead outs here. And I could, but I won't, it'll make the screen a lot busier, but apply a third circle gauge up to the top lead out here. So this is a new feature, yes, and we're kind of, it's now part of the 3.65 software release, and that was only released a number of weeks ago. So as a plug, just to make sure that you upgrade your MVIQ Flame handsets, if you have an analyzed model, this radius gauge is part of that release and is available if you were to want that feature on your inspect or touch models as a paid for feature. So we've taken you through not all of the measurement types, but some of those that are new, but also require a little bit more thought in terms of making sure that the cursor placements are correct in order to extract the data that you need from the image. So I really wanted to kind of gather some more information from you in terms of which features, which measurement types do you regularly use in your tasks, in your workflows. So as I'm talking, please do, if you can, just press the buttons, press those that are most applicable to you. Press as many that are applicable to you in your workflow, and submit those to me, please. That information is very useful for us. Of course, I'm cognizant that some of you on the webinar might not be inspectors, might not be operators of the borescope, so there is a button there for those that aren't applicable. Okay. Just give you a little bit more time for moving on. Okay, thank you. So good range. Thank you. Oh, I need to stop sharing. There we go. Yeah, so good range. Basically, there's an entry for all of the different types. Wasn't expecting so much in some of the features, but yeah, thank you very much. So it's most of you must be users of the MVIQ, because I know there's certain features that are only available, for instance, depth profile and area depth profile on the MVIQ. But good to see. Thank you very much. Very good. We'll move on now to the next feature. I know we're running low on time now, but we've afforded some time to take you through questions and answers. So I'll pass you back on to Tom. Thank you.
Yeah, thanks, Mr. Gambers, and thanks, Clark Bendel. So, everybody, I hope you've learned something today. I do see a couple questions here that we can try to get to, and we'll have our experts answer those. So, the first one, maybe I'll take. That's the question of the yellow tip. So, Clark showed a yellow phase measurement tip earlier. The question is that a new tip? Yes, and just to let you guys know, we will many times work with customers with specific applications, and if we can, we'll in some cases develop a way to solve those problems. And so the yellow tip has been helpful in that area. That's something that you'll see added to our portfolio, so look for that in the future. And then before I ask the next question, Tom talked about, as an example, radius gauge is now part of the Analyze system, because we do include with Analyze our onboard features every time we do a software update. So if we have a new measurement type like radius gauge, it'll be included there and it can be purchased on the inspector to touch. But also good to know is that we include those for 90 days as a free trial on all the tiers of our product. So if you saw something there, as an example, radius gauge that you want to try out, if you upgrade to 365 on your system, you'll see that's available for you to try out for that period of time. Here's a question on measurement. What is the measurement accuracy? So this says an absolute number. So in other words, how accurate can we measure with our system? Clark, do you want to take that one?
Sure. Yes, this is a common question that we get a lot. And unfortunately, there's not a simple, straightforward answer to it. You know, under the sort of the best case conditions, if you're up really close and following the guidance we've provided, you typically can get, you know, repeatable measurements to within about, you know, roughly 1,000th of an inch repeatability, which I believe is about 0.025 millimeters. But it really depends on the measurement application, the surface finish, and the techniques that you use. So really the best thing, if you have a really critical application, if you're able to do some testing on some samples that are representative, sort of a gauge R&R, that's going to give you the most realistic numbers on accuracy for that specific application. We do in the 3D measurement handbook, which I believe is linked in the related content section. We have some results of some third-party testing on a measurement test block, which will give you some sense of sort of what can the system do under best case conditions. And then again, results are going to depend on your specific application.
Yeah, thanks, Clark. And so folks, take the time to download that measurement handbook. It's a really good piece of literature to read through. It's got a lot of great information in it. So go ahead and do that if you're interested in measurement. Question here that I'll maybe take, what is real 3D measurement? You know, is it 3D stereo? Is it 3D phase? Is it both? So 3D measurement, when we talk 3D, just so everybody knows, even traditional stereo is a sort of a 3D math technique to compute tip to target distance so that we can come up with measurement answers. But what we mean when we say real 3D measurement, we wanted to make sure that that's sort of an industry name that tags to ourselves, because what we do, as you've seen here today, is we create this 3D map, this fully surfaced 3D point cloud, and you can learn a lot from that. You can learn whether you are actually measuring what you think you're measuring. You can judge the measurement is how noisy it is. Are the cursors placed where they should be placed? And a lot of manipulation to really the point there is for you to be able to study that measurement. And when you make an answer, whether it's in or out of limits as an example, you're confident in that because you've got these tools that can help you do that. So that's really what real 3D measurement means. Another question I have here, maybe for Tom or Clark, is what is planned in the future for real 3D measurement? So where are we going with this? Is there anything you can share there relative to that question?
Sure, maybe I can speak to that a little bit, Tom. So, you know, as you've seen in this webinar, we've got these new tips that we've developed, the green being a fairly new one, the yellow being a very new one. And so I would anticipate, you know, as we hear from more customers and understand different needs, that we would develop different models of tips to maybe expand the capability range, either on the small side or the large side. You know, we're also always looking at specific applications and whether the measurement types that we currently have can be used to address those applications efficiently. And if not, you know, we may look at developing a new measurement type, such as the radius gauge, that can more efficiently address those applications. So I would sort of think in those two areas are likely to see some evolution over time here.
Yeah, thanks, Clark. And maybe I'll add there that, you know, folks, if you have hard measurement problems that you're trying to solve, we are always willing to look. So if you get a hold of your local sales representative, call into our technical help support desk. They're always there to help and provide us with kind of an understanding of what you're trying to do there, even provide some images with measurement data on those. We can take a look at that, and we've done so in the past, and that's led to some of these developments. Just before, I have one more question that I see here, and just before I ask that question, letting everybody know we're a little bit over time. If you want to stay on and ask more questions, we're happy to stay here and answer them. So just keep feeding them into the system here. Otherwise, we'll wrap up in a second if I don't see any more. But in this case, there's a question on software, right? Does 3.65 software, is that available for the gray handset? And so just for everybody's understanding, the original Mentor Visual IQ that we launched back in 2014, the handset was gray. It had a little bit different technology in it. As technology advanced, we came out with the Flame handset, which was a more capable system. And so gray, we stopped doing software development on, I believe it was on 3.19. So any of the stuff you're seeing here at 3.65 and anything after 3.19 is only available on our Flame handset. The good news is you don't have to buy a brand new system. We have an upgrade path to go from gray to Flame. So that's something you can look into, talk to your local sales representative, and it's a very cost-effective way to get into some brand new technology, which is quite frankly superior to what the gray was in the past. Hopefully that answers that question. Just holding on here for one more second. I don't see anything popping in. If it does, I'll answer it, but just short of that happening, I just want to say that we thank you very much for sharing your time with us today, wherever you are in this big world. Please reach out with any other questions that you find here. Go to the website, reach out to your sales folks, come into our technical support desk. We love the questions. We love developing new technology, and we generally do it with input mostly from our customers out there on their applications and the problems. So please continue to share that with us. And with that, we're going to sign off, and I hope you have a great day and happy inspecting. Bye for now.